Calculus 3 video lecture number 25 on triple integrals in spherical coordinates. So we're going to look at a new coordinate system in which we're going to evaluate triple integrals, and it's defined as following. So in spherical coordinates, a point is represented by the ordered triple rho, theta, phi. So in case you're not familiar with some of these Greek letters, this first one here is rho. Theta you should know, and the last one is phi. All right, so here's our point in our three-dimensional coordinate system, and it's represented by rho, theta, and phi, and I'm going to demonstrate exactly where they all are, okay? So first off, rho is the distance from the origin to the point. And as a note, rho is always greater than or equal to 0. So we don't allow for it to be negative. So rho is this distance here. I'll highlight it too for you to see, from the point to the origin. All right, theta, that's the same as before. So we'll add in theta to our picture. So sweeping out from the positive x-axis, that's where theta would be. I just drew it in the xy plane to make it easier for perspective. And then what about phi? This is a new one. So phi is the angle that's between the positive z-axis and the segment from the origin to the point. Okay, so the segment from the origin to the point, I've already highlighted in blue. So phi is the angle between the positive z-axis and that segment. So let's add that in our picture. So phi is this angle right here. All right, now as a note of caution, we restrict phi to always being between 0 and pi, not 2 pi. And don't worry, since theta can range between 0 and 2 pi, it'll cover all of the possible points that you need to represent using spherical coordinates. All right, good. So this leads us to some nice relationships, because I'm sure you're curious, how are we going to convert, right, between our two coordinate systems? Well, we have 3 now. Look at us, so fancy. So here I have this point represented using spherical coordinates. But notice I can make a right triangle here. And this side is z, right, working in cylindrical or rectangular. Also, by alternate interior angles, this angle inside the triangle is also phi. So now we're almost ready, almost. This distance down here, the base of that triangle is r, that we know from cylindrical, which is also that distance up here, r. Okay, so easiest relationship I noticed in the triangle, just working with that triangle, involves cosine of phi, right? So z is going to equal rho cosine phi. Let's start with that. So z is rho cosine phi. Notice here, I'll come in and help you in case you need it. So z is the adjacent side if I'm looking at this phi, okay? Adjacent over hypotenuse. Now what about r, little r? So that's going to be rho sine phi. And then all you do is use your previous relationships from polar or cylindrical, same thing. X is r cosine theta and y is r sine theta. So now putting it all together, if you want to go from spherical to rectangular, we have the following. X is equal to, normally it's r cosine theta, so you substitute in rho sine phi for r cosine theta. Y is going to be rho sine phi sine theta. And then z is the one that's short and sweet, rho cosine phi. Okay, so here's our relationships. Basically, if you just remember z is rho cosine phi and r is rho sine phi, then you're in business, right? Because the polar ones you should have burned in the brain at this point. So if you just learn those two new ones, then you can get whatever you need. Also, rho squared is equal to x squared plus y squared plus z squared. Look back at the picture so you believe me, okay? So notice here we have this right triangle. So rho squared is equal to z squared plus r squared, but r squared is just x squared plus y squared, if you'll remember. So that's where that comes from. And then all of our other relationships hold for theta, right? So tangent of theta would be y over x. And then for phi, you could either use cosine of phi is z over rho, or you could use that tangent of phi is r over z, either one, okay, if you're trying to find that angle. So before we get into the calculus, let's just practice a few examples converting back and forth and graphing so we can get comfortable in this coordinate system. So first one, we're going to change this point 2 pi over 2, 3 pi over 4 from spherical to rectangular. So right underneath what each one represents so you don't get it all jumbled up in the brain. So this is rho, this is theta, this is phi. It's currently in spherical. They want x, y, z. They want rectangular. So x is rho sine phi, so sine 3 pi over 4, cosine theta, pi over 2. Well, I know cosine pi over 2 is 0, so this is just 0. Y is going to be 2 times sine of 3 pi over 4 sine of pi over 2. Well, sine of pi over 2 is just 1. And then sine of 3 pi over 4 is rad 2 over 2 times 2 gives me rad 2. And then z is going to be 2 cosine 3 pi over 4. So that's going to give me 2 times negative rad 2 over 2, so just negative rad 2. So in rectangular coordinates, this point is 0, rad 2, negative rad 2. All right, very nice. Let's look at another example where we're going to go the other way. So this time, this point here is written in rectangular. Now we need to write it in spherical. So this is x, y, z. All right. First thing you have to do is find rho. So rho squared is x squared plus y squared plus z squared. So I'm just going to take the square root right off the bat. So rho is going to equal the square root of negative rad 3 squared plus negative 3 squared plus negative 2 squared. All right. So that's 3 plus 9 plus 4, which is 16. Square root of 16 is 4. Ooh, so snazzy. Okay, so I've got rho. Let's get theta. Theta is easy to get because I know tangent of theta is equal to y over x, right? That's not going to change. So I have negative 3 over negative rad 3, which reduces to just rad 3. Now let's think here, if we were just in the xy plane, right, both x and y are negative, which means we would be in quadrant 3. So we have a pi over 3 reference angle since tangent's rad 3, but my actual theta is going to equal 4 pi over 3 since I need it to be in the third quadrant in the xy plane. Okay, so I've got rho, I've got theta, I just need phi. And it's up to you. I think the easiest thing is just since you need to put to memory z is rho cosine phi, and we have z and we found rho, we're ready to roll. So cosine of phi is going to be z over rho, which is going to be, in this particular case, let's see, z is negative 2. Rho was 4. Oh, how nice. Someone wrote this problem who loves us. Negative 1/2, which means phi is going to be equal to, and then now you don't have to play around because cosine's going to be bounded between, cosine inverse, the range is between 0 and pi, and that's what phi is always going to be between anyway, so you're fine. So if cosine's negative, I'm going to be giving a quadrant 2 angle, something between pi over 2 and pi, so it's going to be 2 pi over 3. Okay, so putting it all together, 4, theta comes next, okay? Just think theta's in the same spot that it was when you were doing cylindrical. And then phi is last, the newcomer. All right, very good. Now, when is it a good idea to use spherical coordinates? When will you find them useful? Well, they're especially useful when the surface is symmetric with respect to the origin. Okay, so what sort of surfaces are symmetric with respect to the origin? Spheres, surprise, surprise. Spheres work nicely in spherical. And cones. Cones have a really cool representation, so we'll look at that later. Okay, so let's look at some graphs now. Sketch the graph of the following, and these are all in spherical. So we have rho equals 3. Well, right off the bat, if rho is 3, maybe you can imagine that you're just going to sketch out, because phi and theta can be anything, a sphere of radius 3. Or maybe you don't like that. You want to do some more math. You like to write stuff down. So then you'd have rho squared is equal to 9, right? If I square both sides. And rho squared, remember, is x squared plus y squared plus z squared is 9. So now you can see, oh yeah, it was a sphere. Centered at the origin, radius 3. But look at what a clean representation you have. Just rho equals 3, right? When you use spherical coordinates. Okay, let's sketch it out. Always put a little bit of labeling on those axes. And it's the full sphere, right? So top half and bottom half. Okay, moving on. Theta equals pi over 4. Okay, so notice rho is missing. Rho can be anything. Phi is missing. Phi can be anything as long as theta is pi over 4. So let's think about what that would look like if we were to just graph it in the xy plane first. Okay, so if theta was pi over 4, that means you would sweep out an angle of pi over 4 this way. And then rho can be anything, and phi, well, remember, phi is naturally restricted between 0 and pi. That's how we define that angle. So phi can sweep from 0 all the way down to pi, but that's it. I wanted to highlight that instead. That's what phi can cover. So what ends up happening is you get what looks like a plane, but technically it's just a half a plane. Can you have half of something that's infinite? Yeah, we're doing it. Because it doesn't go over here. The plane does not extend back there. Does that make sense? So I'll just call it a half plane. Nice. Now here's one that you're going to want to put to memory because it's going to come up so much. Phi equals pi over 4. So let's imagine what's going on here. Phi is pi over 4. That means the angle that this surface makes with the positive z-axis is always pi over 4. But there's no restriction on rho, and there's no restriction on theta, so it can spin round and around. So pretend this is an angle right here. This is pi over 4. And we can spin round and around, right? Theta can be anything, and it can extend up as much as you want. So this is a half cone. All right. If you needed the bottom half, could you figure out what the equation would have to be? It would be a separate one. If you needed the bottom half, then you would have phi equals 3 pi over 4. Correct. All right, last little graph, rho equals 2 cosine phi. So maybe it's best if we just convert this to rectangular to get a feel for what's going on. I'm going to multiply through by rho, so I'll have rho squared equals 2 rho cosine phi. And then rho squared is x squared plus y squared plus z squared. Rho cosine phi is z, right? So this is equals 2z. And then I can complete the square already. I can tell I got a sphere. So this is x squared plus y squared plus z minus 1 squared equals 1. So we've got a sphere. Woohoo! Where's the center? 0, 0, 1. What's the radius? It's 1. Ooh, this is going to look cool because it's sitting up on the xy plane, right? It's just going to touch it at the bottom. X, y, z. So we'll have to go up to 2. so here's the sphere, the radius is 1, and its center is at 0, 0, 1. Very nice. All right. Just a couple more exercises and then we'll get into the calculus, I promise. So let's change the following ordered triple. It's in cylindrical. We're going to change to spherical. So if it's in cylindrical, just remind yourself, this is R, this is theta, and this is Z. Well, theta you leave alone, right? Okay. So all I need is rho and I need phi. So remember, rho squared is x squared plus y squared plus z squared. But x squared plus y squared is r squared, right? So that means rho squared is going to equal the square root of, now come back to the point here. So r is 1 and z is 1. So 1 squared plus 1 squared, that's 2. So rho is rad 2. And then all I need is phi. So we can just use z equals rho cosine phi, right? Or you could just already isolate cosine phi. That equals z over rho, which is going to equal, so z is 1, and then we just got rho. Thank goodness we did it in that order. Okay, so cosine phi is 1 over rad 2, so that means phi is pi over 4. Remember, theta stays the same and it doesn't change spots. So you have rad 2, pi over 2, and then pi over 4 last. Okay. What's the only order we haven't done yet? You guessed it, spherical to cylindrical. Let's do it. So this is in spherical. That means this is rho, this is theta, this is phi. So I need r and I need z. Theta stays the same. Well, r is rho sine phi. This is easier, right? You don't have to think, you just plug everything in. So 4 sine pi over 3. So sine of pi over 3, that's rad 3 over 2. So that's 2 rad 3. Theta doesn't change, so theta is still pi over 4, and then z is rho cosine phi. So that's going to be 4 cosine pi over 3. So 4 times a half, which is 2. So putting it all together, you have 2 rad 3, pi over 4, and 2. Good. Okay, now as you've seen when we did triple integrals, a lot of the times they were used to find volumes of solids that were enclosed by different surfaces. So it's going to be important that we can understand how to graph and intersect surfaces in space and also restrict them. So sketch the solid described by the following inequalities. So phi is going to be bounded between 0 and pi thirds, and then rho is less than or equal to 2. So we saw that phi equaling a constant described the graph of a cone. So since phi is between 0 and pi thirds, then that means it's inside this half cone. That makes an angle of pi thirds with the positive z-axis. Rho less than or equal to 2 means we're inside a sphere, right, of radius 2. So let's draw what this solid would look like. So start off, make your angle of pi thirds with the positive z-axis. And you want to indicate that you know what the angle is, okay? Don't just draw your cone willy-nilly and think it'll work out. So I'm going to say this is pi thirds, okay? So it's everything inside there, and then also inside the sphere whose radius is 2. And that sphere is going to be centered at the origin, so you could imagine it would come down like this, around and around. Anyways, it doesn't matter what the rest of it looks like because we have to stay inside the cone. So what are we dealing with? I want to draw this a little more curvy. Cute. We're dealing with inside the cone and inside the sphere. So it looks like an ice cream cone, snow cone, something like that. Very good. Okay. I think we're ready to roll now. So we're going to look at integration using spherical coordinates. And remember, dv changes depending on what coordinate system you're in. So when we were in rectangular, dv was just simply dx, dy, dz, no big deal. And then when we switched to cylindrical, we showed that dv was r dz, dr, d theta, which made sense because it was very similar to polar. Now, what is dv going to be in spherical? Well, what we're going to do first is look at an increment of volume in spherical coordinates, which is shown below. So I'm going to look at delta V. And what is delta V? A change in volume for some solid described using spherical coordinates. So that's going to be my delta V. And I need to label this diagram a little bit more so that we can refer to it. So I'm going to call this point over here S, this point in the front P, this point over here is R, and this point right here is Q. Okay, very good. Now notice here we have some arrows designating changes that are going on. We'll fill those in momentarily. I just wanted to start with this part so far. So delta V, the change in volume, that increment of volume can be approximated by just taking its length times width times height, right? It's not a perfect rectangular solid, so this is an approximation. So I could find it by taking the length of PS times the length of PR times the length of PQ. And what I'm going to try to do now is express each of those segments' lengths, PS, PR, PQ, in terms of rho, phi, and theta. Okay, so I'm going to start first with PS, magnitude or length of PS. Okay, that's an arc. It's not technically straight, yes? And what is it dependent on? Notice, as you move from P to S, that is a change in theta. Notice it's mirrored in the XY plane, delta theta, down here. This is delta theta. Can you see that? Let's zoom. I mean, why not? Now's the time to do it. Okay, that's your delta theta. So PS is an arc. It's dependent on theta, which changes. And we know our formula for the length of an arc, S equals R theta. So this magnitude of PS is going to be R times delta theta. Good, but remember we're trying to work in spherical. So magnitude of PS, instead of R, I'm going to write rho sine phi delta theta. Okay, so this R is my rho sine phi. Okay, that one's done. Let's move on to the next arc. The next arc is PR, so magnitude of PR. That is also an arc. What is it dependent on? Well, notice from P to R, what's changing? How do you get from P to R? That's a change in phi. So this is your delta phi. Right, remember this angle here, phi, is measured from the positive z-axis to the segment that contains the point. And if I move from P to R, I'm just changing phi to capital R. Remember, our lowercase r, if you're thinking back in cylindrical, this is your little r, right? Your lowercase r. Okay, good. Maybe I'll add this here so you could see that's your delta theta going on right there. Okay, so delta phi, I'll even add it in right here if you want to see it. This right here, this is your delta phi. Beautiful. All right, so PR is also an arc. That means its length, PR, is going to be given by, now notice in this case, the distance that PR is from the origin doesn't change, and it's equal to rho. Yes, shall we label that in there? Why not? I mean, we've got a lot to label. Let's do it. So this is rho right here. That's rho. So PR is equal to rho delta phi. All right, that's different than PS, yes? So PS was determined by R delta theta. Do you see the difference? Okay, Now last one is PQ. So that PQ, well, that's not dependent on any angle changing. That's just a change in rho. So that's delta rho. Let me make it more rho-y. Good. So PQ is change in rho. Okay. Anything I need to add to the diagram? I don't want it to get too cluttered. This is Z, obviously, right? If you're thinking back to rectangular or cylindrical. I've got my delta theta. Yep, everything looks lovely. Okay, so we're going to put it all together because remember, delta V was the product of all of these. So I'm going to take rho sine phi delta theta times rho delta phi times delta rho. So where does this put me? Delta V is approximately equal to rho sine phi delta theta times rho delta phi times delta rho. And then what do? Well, we take a limit, yada, yada. So in the limit, then we end up with, or we have dV is equal to, now notice, here's a rho, here's a rho. So I've got a rho squared, I've got a sine phi, and then you'll have d rho, d phi, d theta. That's typically the order that you'll see it in. Or sometimes we'll do dV equals rho squared sine phi, don't forget that. And then you have d rho, d theta, d phi. But usually it's the angles that are on the very outside, okay? Yeah, so just like in cylindrical, you had to add that extra r. Now you have to add a rho squared sine phi. So fancy, right? But hopefully you see why it's not just arbitrary. When we get to the next video, you'll really believe it in your heart of hearts. Now I mentioned spherical coordinates are very useful with cones and spheres, and I wanted to show you this snazzy example here. Okay, so we're going to consider the equation of a cone, z equals the square root of 3x squared plus 3y squared. Okay, well typically we don't have those 3's in front. When we deal with our cone, we just have z equals rad x squared plus y squared, but all this does is change the steepness of the cone, okay? So let's see, how would you convert this to spherical? Well, I know x squared plus y squared is r squared, so let's start there. So z is going to equal the square root of 3r squared, which is just rad 3r, yes? Which means now z divided by r is equal to rad 3 over 1. Do you guys agree? And I mentioned before, if you imagine that right triangle that I first showed you when we were converting to spherical, that tangent of phi is also equal to r divided by z. So since r divided by z, since that ratio is constant, then that means tangent of phi is fixed at 1 over rad 3. So the angle is fixed. Phi is fixed. Phi is equal to pi over 6. So this is your equivalent equation for that half cone when you're working in spherical. Phi equals pi over 6. And what that tells you is it makes an angle of pi over 6 with the positive z-axis. And you don't have to show like any of this computation in the future. Although for the 3 business, you might need to, but I'll show you right now in a hot second which one you're not going to have to show work for because it's going to come up so much. Okay. So what you're going to do is, here's your cone, and then here's phi, which is pi over 6. And if you look at the ratio of z to r, it's constant no matter what point you pick on that cone, right? So that ratio is going to give you rad 3 over 1. There's your little r, there's your z. So lovely. The one that's going to come up so much is z equals square root of x squared plus y squared. Then you would just get z equals r, which means tangent of phi equals 1. So you would say phi is pi over 4. So if you see you have this cone and you automatically know it's phi equals pi over 4, go for it. Don't show work. That one's going to come up so much. All right. Are you ready to integrate? I mean, we've done so much buildup. We might as well at this point. All right. So evaluate the triple integral over E of x squared plus y squared dv if E is the solid below x squared plus y squared plus z squared equals 1 and above the xy plane. Okay, so I know this is a sphere. Radius is 1, and we're above the XY plane. Okay, so let's draw what's going on. So E is just basically the upper half of the sphere, right? Here's 1. Whoa, what coordinate system am I drawing? Z is here. Okay. So this is the bottom, right? Because we're above the XY plane. We're above all this. And then it's below this sphere. It's coming out here. Okay, I think we got it. Yes? All right, so let's set up our limits of integration. Let's do theta on the outside. That's typically how it's going to go. I'll tell you what each one of them are so you can keep it straight. So theta. What should theta vary between in order to sketch out the upper half of that sphere? We'll look at it. Remember, theta is measuring the angle here, so it looks like it goes all the way around, complete revolution. So theta should range between 0 and 2 pi. Very good. Now what about phi? Well, I only want the upper half of the sphere. And remember, it measures from the positive z-axis. So phi needs to stop at pi over 2 and start at 0. So those are our limits for phi, 0 to pi over 2. And then what about rho? Well, similar to polar or other situations, you can draw an arrow. So start at the origin, go until you hit the edge of your solid. What is rho equal to? Where does it start? Where does it stop? It consistently starts at 0, stops at 1. Yes? Okay. Now, I have to change everything into spherical coordinates. So x squared plus y squared, I know that's r squared, but in spherical, r is rho sine phi. So I have rho sine phi squared. And then remember dv, I'll do that in a different color so you know that's just for dv. dv is rho squared sine phi d rho d phi d theta. All right, so now everyone's accounted for. Before you have a panic attack, notice all of your limits are constants, yes? And your integrand can be written as a product of functions exclusively of rho, phi, and there's not even a theta. So we can break this up into just 3 integrals of functions of a single variable, no big deal. So if you were to actually sit down and compute it, which I already did before, you'd have 0 to 2 pi, that's for d theta. There's no thetas in there, right? Cool. Then we have 0 to pi over 2. This is for all of our phis. So we've got a sine cubed phi going on, d phi. Let's just talk about how we'd integrate it. Do you know what to do? You'd break off one of those signs. You'd replace the sine squared with 1 minus cosine squared, and then you would do a u sub. Got it? Good. And then last one, 0 to 1, rho to the 4th, d rho. All right, manageable. I already know this first guy. Don't even waste a second of your life thinking about it. It's 2 pi. And then the other two you can do no big deal. All right, so you should end up with 4 pi over 15. It really is the answer, even though it doesn't want to be boxed. Very good. Okay, let's look at something a little more tricky, right? That was too easy, just a sphere, come on. Here's an integral. It's given to us in rectangular coordinates, and we need to rewrite it using spherical. Ooh, some of my favorites. So start off by drawing what the base region's gonna look like. In this case, it's the xy plane. So 0 to 3 are my limits for y. And then 0 to rad 9 minus y squared are my limits for x. So let's see what's going on just in the xy plane. Okay, don't get carried away. Start simple. XY plane, y is only between 0 and 3. And then x is between 0 and rad 9 minus y squared. Okay, so that's going to be the right half of a semicircle. Radius is 3. But we're only going to stay in the first quadrant since y is between 0 and 3, yes? So x equals rad 9 minus y squared. Beautiful. Now let's look at the limits on z. So this is the trickier part. So for z, lower limit is z equals rad x squared plus y squared. I know that's going to be a half cone, right, since we only have the positive radical. And then the upper limit is z equals the square root of 18 minus x squared minus y squared. Well, that's a half sphere. Okay, so let's draw what this would look like. And we're only dealing with the portion that's going to be in the first octant, right, since x and y is restricted to the first quadrant. So we've got something bounded below by a cone and bounded above by a sphere. I feel like we've done something like this before. Call me crazy. Okay, here's 3, 3. It's bounded above half sphere. The radius of that half sphere is going to be square root of 18, which is 3 rad 2. So I'm saying that's 3 rad 2 right there, people. Okay, good. So here we've got the cone. The cone is making an angle of pi over 4 with the positive z-axis. Maybe something like that. There's the cone. And then the half sphere, I'm not going to draw all of it, just the part that our graph lives underneath. That should touch. Yes, yes, yes. Okay, very good. And obviously the cone keeps going, but we're not interested in that portion, only what's inside here. So let me shade it in so we're all crystal clear on what's going on. So above the cone, underneath that upper half of the sphere. And then just as a reminder, this is a good idea, sketch out the fact that you're only working where x and y are positive, okay? Good, so let's set up our integral now. Outer bounds, let's do theta. Okay. So theta is going to range between, notice for theta, you're going to start at the positive x-axis and at the positive y-axis. So that's just going to be from 0 to pi over 2. Now what about phi? Well, phi is going to start at 0 and end at pi over 4. That's phi. Phi is going to go from 0 to pi over 4. And then last but not least is rho. Okay, you could draw your little ray if it helps. Start at the origin, go until you hit the end of your solid that's swept out by rho. So it looks like it's going from 0 up until the sphere, yes? So from 0 up until, now what would the sphere's equation be in spherical coordinates? You just get precisely what the radius is, which is 3 rad 2. And then I have to change the integrand so that it also is in terms of spherical coordinates. So x squared plus y squared plus z squared, that's rho squared. And then dz dx dy, that's going to be another rho squared sine phi, d rho, d phi, d theta. Okay. And that is all they asked us to do. They just said rewrite it. They didn't say evaluate it. Okay. But in case you'll lose sleep, I'll tell you what it is if you want to check it. It's going to be 486 pi times rad 2 minus 1 all over 5. I'm not promising the answers are going to be cute, but they're going to be doable. All right, now we have a lot of options, right? We have rectangular coordinate system, spherical, and don't forget about cylindrical. And the choice of coordinate systems often has a major impact on how difficult it is to actually compute or evaluate the integral. And when we first discussed cylindrical coordinates, we rewrote this triple integral from 0 to 1, 0 to rad 1 minus y squared. X squared plus y squared is the lower limit. That's your paraboloid opening upward up until a cone. We rewrote it as the following, triple integral and cylindrical. I don't need to read it to you. You can all see that. So what we're going to try to do is rewrite the same integral, but this time using spherical coordinates. So I'm going to draw everything out from scratch again. We'll just start from rectangular, and then we'll go to spherical. That's probably the easiest way. okay? So first thing I notice is we'll draw the base region in the XY plane. It's super similar to the problem we just did. We're gonna stay in the first octant in 3 space. And we're in the first quadrant in just the XY plane, right? So y is bounded between 0 and 1. And then x is given by the right half of a circle of radius 1. So we are just right here in the XY plane. That's the base region. Now look at the lower limit for z. So z equals x squared plus y squared. I mentioned that's a paraboloid. That's the lower limit. And then z equals rad x squared plus y squared. That is a half a cone. Upper half. So let's graph it. And remember, this only lives in the first octant, but I'll draw like the rest of the surface just to give perspective, okay? But I'll just shade in the front portion towards us. So here's 1. We know this cone, famous guy. Here it is. And then the cool thing is I know the cone is bounding it above because of the way the limit's written. So the paraboloid is bounding it below. I'm really going to exaggerate that so you can see what we're finding, okay? So let's just pretend this is the portion that's going to be in the first octant, okay? Very good. So now let's write out our triple integral. Here we go. So this one's for theta. Theta. Where does theta need to live between? Well, only where x and y are positive, so theta is going to be between 0 and pi over 2. You could also just use the xy plane to help you. What about phi? Don't start at 0. Don't start at 0. Phi starts here, and then it ends down there. Right? Look at your solid. It doesn't start when phi is 0. It starts when phi is pi over 4. And it stops, well, this paraboloid goes all the way down to pi over 2, doesn't it? Okay, so be careful. So pi over 4 to pi over 2. Now it's time for rho. Okay, shall we draw some arrows in there to help us out? Perhaps that's a good idea. So rho starts at the origin and then go until you hit the edge of your solid. It looks like rho stops when it hits the paraboloid. So rho starts at 0 and then it stops at the paraboloid. Well, how in the world am I going to write the equation of the paraboloid in spherical? Well, this is how. So remember, rho goes from 0 to the paraboloid. Okay. Well, the equation of the paraboloid is z equals x squared plus y squared, which is r squared. Let's see if we can get to spherical somehow. Well, z is rho cosine phi. That equals r squared. R squared would be rho squared sine squared phi. I can cancel out a rho just like I'm allowed to do in polar. Bye-bye. Then now I have rho equals cosine phi divided by sine squared phi. Whew. And then think ahead, right? We're going to integrate this. I'm going to break it up and write it as cotangent phi, cosecant phi. Yes, you have to do it this way. You cannot leave it cosine phi over sine squared phi for me on an exam. Clean it up. Okay, so upper limit's going to be cotangent phi, cosecant phi. Yay! Wonderful. Now let's fill in the rest. Move this out of the way. So let's see here. What was the integrand? The integrand was, oh my goodness, x, y, z. So we got to switch that now. Okay, so x is going to be rho sine phi cosine theta. Y is going to be rho sine phi sine theta. Z is rho cosine phi. Phi. And then dv, rho squared sine phi, d rho, d phi, d theta. So let me highlight the fact this is your dv and then this is XYZ. So you know where everybody came from, okay? I don't think this was your best bet if you're gonna evaluate it. I would go with cylindrical. What about you? Okay, the fun's not over. I got one more for you. Set up integrals in all three systems that represent the volume of a cylinder of radius 2, height 3. Okay, let's draw it out and then set it up. Obviously, we can compute the formula directly. We know how to find the volume of a cylinder, but we're going to set up integrals that would let us do this. X, Y, Z. You can check that you set them up right, though, by evaluating it. Okay, so radius 2, and then the height is 3. 1, 2, 3. Okay, so here's my cylinder. And the height is 3. Very nice. This one's going to be a wee bit lower. Okay, beautiful. So let's start off, we'll do rectangular first. And I want the volume of that whole cylinder. So let's imagine the base region in the XY plane. They didn't specify the order, so we could do whatever we want. Do you need me to draw it out separately? Maybe not, right? Maybe you've done enough of these circles in the XY plane, now you got it down cold. So radius is 2. We have the full circle this time because we want that whole cylinder. I mean, come on, we got the whole thing. Bam. Okay, so you could do x on the outside, y on the outside, up to you. I say let's solve y in terms of x, so it would be rad 4 minus x squared for the upper half, and then negative rad 4 minus x squared for the bottom half. So here we go. So limits for x, those are going to be my constant limits on the outside from negative 2 to 2. Y is going to be bounded below by negative rad 4 minus x squared, above by positive rad 4 minus x squared. And then z, what is z bounded between? We'll just look here at our solid. So z starts at 0, stops at 3, right? That's it. Just constants are bounding it, 0 to 3. So this is dz, dy, dx. All right, cool. Not too painful. Now let's try cylindrical. I have a hunch this one's going to be the best one because it is a cylinder whose volume we're trying to find. Okay, so let's do theta on the outside. So I'll write down here. That one's for theta. So theta is going to range between, just look at your xy plane. Look at your xy plane and make it go polar. So theta is going to go from 0 to 2 pi. Now this is r. R is going to go from 0 to 2. And then this is z. Z is going to stay the same, 0 to 3. And then don't forget dv now is r, dz, dr, d theta. Good. Painless so far, right? You might be thinking, are you kidding me? Why is this so easy? Okay. Well, spherical is just going to take a wee bit more work. And first I'm going to explain why. Okay, now remember rho is going to measure out the distance from the origin, right, to a point on the surface. Now watch this. I'm going to draw out a few rays that demonstrate rho. So rho's going to go maybe to here, right? Stops at 3, stops at the top, stops at the top, stops at the top. So the plane z equals 3 is determining it up until here. And then what happens past that point? Well, now the side of the cylinder is determining the length of rho. And the side of the cylinder is given by r equals 2. So what I need to do is split up my integral because I have to split up how I define the limits on rho. So the top of the cylinder, when it's determining rho, that's given by z equals 3. And if I want to write that in terms of spherical coordinates, that would be rho cosine phi equals 3. So rho equals 3 secant phi. So that's good. Now when the side of the cylinder is determining rho, that's when r is equal to 2, right? Look back at the picture. So r is rho sine phi. That would equal 2, which means rho would equal 2 cosecant phi. Okay, so we're almost ready to get going. Let's set it up. I'll put the limits for theta on the outside. So theta is going to go from 0 to 2 pi. Now what about this first integral for phi? And this is going to represent the top, this first one here. Well, notice the top is determining what rho is up until phi is equal to whatever angle this is. Yes? The top is determining the length of rho from phi being 0 up until wherever that is. Can I figure out wherever that is? Of course I can. Of course. We've got this snazzy little right triangle, don't we? The top, the radius is 2, the height is 3, and here is phi, which means tangent of phi, why did I write a theta? My goodness. Phi, which means tangent of phi would equal 2/3. So until phi is equal to tan inverse of 2/3, the top, which is rho equals 3 secant phi, is determining the length of rho, okay? So we're going to go from 0 to tan inverse of 2/3. That's for phi. And then now, limits for rho are going to be from 0 to 3 secant phi. That's for rho. And then dv is rho squared sine phi d rho d phi d theta plus, so that one's for the top. Now this one's going to use the side. Rho is going to be determined by the side. So theta is still the same, 0 to 2 pi. Now this time for phi, be careful, go back to your picture. So it's going to pick up where the other one left off at tan inverse of 2/3, and it's going to go all the way until phi is pi over 2 right there, yes? When it hits the positive y-axis. So we're going to go from, I need more room, okay, from tan inverse of 2/3 up until pi over 2. And then there, rho is determined by the side, which we found was 2 cosecant phi. And then I got to smash in rho squared sine phi d rho d phi d theta. Ooh, that's a good one right there. Anyways, it's no surprise cylindrical worked the best for a cylinder, eh? And that concludes the lesson on spherical coordinates. So stay tuned. The Jacobian change of variables in multiple integrals is coming up. Exciting stuff.